Okay. So let's review chapter 12 today. Oh, by the way, do you have the syllabus? You can find the syllabus on my website, right? So in case you want to know, the percentage of each exam, etc., you can find it. So chapter 12 is on vectors, lines, and planes. To review, suppose you have a space coordinate and a point, let's say 1, 2, 3, and another point, let's say -1, -1, -1. Then you can connect these 2 points and give you a vector. Right, so do you remember how to write on the components of this vector? The vector between 2 points is the difference between their coordinates, right? So it would be, can anyone tell me the first one? Do you remember this, or you need me to remind you? Yes, it's 1 minus -1. And the second one?
3.
3, 2 minus -1. And the third one is 3 minus -1. So that would be 2, 3, and 4. Alright? So that's how we find the vector's components. Just the end minus the beginning. And if you want to find out the length of this vector, do you remember how to do that? You have to use the 3D Pythagorean theorem, right? Do you remember what that is? The square root of something. Did you learn this? Is this really a review, or it's new to you? You have all taken Cap 2, right? Not too many years ago. So, can you tell me what that is? If you have the 3 components of a vector, then how do you find out its length?
X squared plus y.
Very good. It's x squared plus y squared plus z squared, right? So in this case, it would be 2 squared plus 3 squared plus 4 squared. And if you add them up, this is 4, this is 9, this is 16. So you get a 4 plus 16 is 29. Alright, that's how you find out the length. And there is something called a dot product. Let's say G equals 2, 3, 4, and U equals 1, 0, 2. We can find out something called a dot product. That's like the product, but because of the 3 components, you have to do 3 products then add together. Do you remember that? So do you know how to do the dot product?
2 into 1 plus
2 times 1 plus 3 times 0 plus 4 times 2. Very good. So you will see this is 2, 0, 8. And that's a dot product. Alright? And what is dot product for? Do you remember the geometrical meaning of dot product? If U and V has 0 dot product, what does that imply geometrically? It's perpendicular, yeah. If it's parallel, then it's pretty much a dot itself. Right? If it's just dot vector itself, then you get a bunch of squares. You won't get 0. if their dot product is 0, then it's a perpendicular. So let me give you a simple example. 1, 1, 0. 1, negative 1, 0. Then you plot it, you will see it's, because it's 0 here, it means the z component is 0, it's in xy plane. Right? So u is like this, and v is 1, negative 1, so it's like that. Right? And they're perpendicular. And that dot product is 1 minus 1 plus 0, which is 0. Right? So this is one example of that dot product equals 0. And that means perpendicular. Or you can say this in a geometrical way. Right? So this is algebraic way, this is a geometrical way, they are the same thing. And that way we can check if two vectors are perpendicular, just use their components. Okay? Alright, there's something harder, it's called a cross product. And the cross product between two vectors is still a vector. Unlike the dot product, which will give you a number. You start from two vectors, but you get one number. Here you start from two vectors, but you get another vector. Does anyone remember what this is? It's a little bit more complicated. Well, it's actually significantly more complicated because it involves a matrix and a determinant, if you remember. You write on this as ijk, which is basically xyz direction. And then, do you remember what you write out here? You write the three components of u. Right? And you call it u1, u2, u3. And this is the v1, v2, v3. Well, this forms a 3 by 3 matrix, and then you take its determinant, which is, well, this ijk, they're actually vectors. Okay, but sometimes you omit that. For example, when you enter ijk in the Weber sign, you don't enter this little arrow because it's kind of hard to enter. So you just enter ijk. And do you remember how to take the absolute, determinant of this of this 3 by 3 matrix? You'll get I times U2 times V3, then minus I times U3 V2, etc., etc. Right? So then you write down here, so I times U2 V3 minus U3 V2, which is the first cross. The second cross is for J, but with J it's some minus because when you do the expansion you have an alternating sign, plus, minus, plus, like that. So for J you cross out these two, well, in your mind, but you don't really cross out because you still need these numbers later. Then you get these two numbers, these four numbers left. U1, V1, U3, V3. Right, then do this cross, which is U1, V3 minus V3 is U3, V1. And the last one is K. And when you do K, you cross out this, then you have these four numbers left. Then you do this cross. Right? Then what do you have? You have U1, V2 minus U2, V1. All right, then you get a vector which has three components, I, j, k, like that. It's a little bit confusing because have so many multiplication and the plus and the minus. So let's see some examples. Let's just use our example here. So for the U and V are just this one and that one. Right, let's find out the cross product. So, write down IJK. What do we write down for the middle row? One, 1, 0, very nice. And then the second row would be 1, -1, 0. Alright, then you have the three components. Well, since it's just in the order of IJK, I can omit IJK. I just write down the three components. Alright, like that. But be careful, the middle one is a negative sign. So I will write down negative sign. Okay? So you won't miss it. Alright, then you get a 3 cross. For I, this one. For J, it's this one. For K, it's this one. Right? So what's the first number for I? Be careful, it's 1 times 0. So it's 0. Minus 0 times -1, which is also 0. So you get 0. Alright? And how about J? It's also 0, because you have 1 times 0 minus 0 times 1. And how about K?
Also 0.
No, that's not 0. Because you have -1 minus 1. And what is that? No, minus 2. Right? It's -1 minus 1. So it's -2. Oh, it's sometimes you have a lot of small numbers, but they are either plus or minus, and you have cancel the signs, etc. Just be careful. So the answer is 0, 0, -2. And that means it's in the negative z direction with length 2. Right? So if you plot it, it will be like the u would be like this, and the v is like that, and then this is u cross. Right? If this is IJK. Like that. Right? It's pointing downward. And this example tells you some property, geometrical property of this cross product. For dot product, if this number happens to be 0, then we know they are perpendicular. For cross product, it will give you a vector, so it won't give you a number 0. And what does this vector represent? Well, as you can see in this picture, this direction is perpendicular to u and v. Actually, it's perpendicular to the plane spanned by u and v. Right? So this cross product always gives you a vector that is perpendicular to u and v. What if u is parallel to v? Then which direction would it point to? There is not a clear direction that is perpendicular to u and v, right? Because u and v in the same direction. So u and v are both here, then everything around will be perpendicular to it. It turns out that when u equals v or u parallel to v, then the third line is just a number times the second line. Right? So for example, this is also 1. Then everything will cancel. 1, 0, 0, 1 cancels, and the last one, 1, 1, 1, 1 also cancels. So if u equals v or parallel to v, then you get 0. Not as a number and a vector. You get a 0 vector. So in that case, if u is parallel to v, then you don't have a direction perpendicular to both of them because it's indeterminate. And that's not a problem because that will be 0. Okay? So if u and v are not parallel, then it will give you the direction that is perpendicular to both of them. Okay? That's the geometrical meaning of cross product. And it's useful because, as we will see in a in the following example that we can use it to find out the equation for a plane. Anyway, let's move on to the. Any question on this? At least you have seen this before, right? Okay. Now let's move on to lines and equations, lines and planes. So what is the equation for a line? Suppose you have a line in space. Then you have to specify the direction of the line for sure, right? But the direction of the line is not enough because you can also parallel, shifted parallel, right? So you also need to specify a point on the line. And this will determine your line, a point and a direction. Then you can draw the line, right? So suppose my point is called R0, a vector which has three components, let's say x0, y0, z0. And the direction is called a vector v, which has three components, v1, v2, v3, like that. Okay, these are 6 numbers, right? 1, 2, 3, 4, 5, 6, like that. Then how do I write down the equation for the line? It turns out that the easiest way to write down an equation for a line is not by writing down something like y equals 2x. Because y equals 2x only represents something in the plane. This is about x, y, z. If you write down y equals 2x, then it's not a line. Because z is arbitrary, then you get a plane. So you have three free variables, x, y, z. So you need to write down two relations between them. It turns out that it's easier to use the so-called parametric curve or parametric equation. So you have to choose a parameter, and there's a very natural parameter. Suppose this is, say, an ant crawling along this line. This is where it starts from, and the time is the parameter. And this v can be regarded as velocity. So after a certain time, it's crawled here, then here, and the history will be here, and in the past. So if you connect all of these points together, then it gives you this line. Right? So we can write down the equation for the line like this. So x naught, y naught, z naught will be the starting point, and after time t, it will move to x naught plus v1t, y naught plus v2t, z naught plus v3t, right? Because this is velocity. Velocity times time gives you the displacement, right? Displacement plus the original place, you get a new coordinate. So this is the equation for the line. Or you can symbolically write down this as R equals R naught plus Vt. That's in the vector form. In the component form, it's just a x, y, z, like that. Okay? But sometimes you need to figure out R naught and the V by itself. Let's see an example. Suppose we have 3 points. Let's say 2 points. What's mine? -1, -1. 1, 2, 3. Last time I told you can find out the vector connecting them. Right? Now let me extend it. So you get a line. Can you write an equation for this line? To write an equation for the line, you have to pick a point on the line as a starting point, then find out the direction of the line. The direction of line is just the vector connecting them. Right? So what is V for this line? That's the thing we found like 10 minutes ago, right? Can you tell me again? 2, 3, 4, very nice. And we have to pick a point on the line. Well, you can pick either one. Right? Let's say -1, -1, -1. Then the equation for the line is x equals y equals what? You write down what is the starting point. -1, -1, -1, right? Then let's move. So you add 1. Say again?
2, sorry.
Yeah, 2. Yeah, 2 t, not just 2, because t is a variable. You have to make it a parameter. And then 3t and 4t. Right? Very good. So you get the equation for that. Now let's see something more challenging. It's called a plane. Suppose you have a plane. This is not very clear. Let me draw a different one. Suppose you have 3 points on the axis and connecting them get a triangle. And the triangle is in a particular plane, right? Let's write an equation for this plane. Well, first of all, how do we write down an equation for a plane? What would it look like? Would it look like something like a parametric curve over parametric equation over there? Do you know the typical form of a plane? Can you give me a plane? Let's say this one. XY plane. What's the equation for that? Very nice. So z equals 0. Because every point in the plane satisfies this condition. And every point, all such points together will give you this plane. Right? So z equals 0. What if you get this? So this is the vertical plane. Going through the axis and the diagonal of xy. So the plane is spanned by this a vertical axis and the diagonal between x and y. Can you tell me the plane equation for this plane? Very good. X equals y. Perfect. And if you haven't seen this, you may say, this is a line, it's not an equation, this is not a plane. Which is true if you are living in 2D. Right? But when we say this is a plane, we mean z is an arbitrary number, because this does not give you any restriction on z. So it means x equals y, and z is arbitrary. So together give you this plane. Okay? So when you see this and that, you have to keep in mind that if you don't have certain variable, then that means that that variable is fixed. It means it's arbitrary. Okay? For example, here, x and y arbitrary. Here, z is arbitrary. So you only need one equation to give a plane. Unlike over there, you need 3 equations with an extra variable, extra parameter. Okay? For plane, we only need one equation. And this equation will be something pretty simple. Just like some x plus some y plus some z equals 0. Oh, not 0, or equals a number. It's 0 only because I pass and the plane passes through the origin. Okay. So, for example, for this one, it's let me tell you how to write an equation for the plane. Suppose you have a plane. Then the plane is determined by two things. The so-called normal direction, which means the direction perpendicular to the plane. Just like the equation for the line, you need to know a direction. But for plane, it's not a plane. The plane does not have its own direction because it's 2D, right? But because it's living 3D, so it has a one particular direction perpendicular to itself. And that's called a normal direction. And if you fix the normal direction, then the only freedom you have is to shift along this. Right? So to fix that, you also need to specify a point in the plane. And we call this R0. So if you have a point R0, then specify the direction N, then the plane is defined by all the points that is, so that this is perpendicular. This R in the plane will be form a vector from R0, so that R0 from R0 to R will be perpendicular to the normal direction. Right? So the plane is defined as the collection of points so that the vector is perpendicular to N. Right? So how do we write down that algebraically? Geometrically it says for any point in the plane, this vector must be perpendicular to N. Right? Do you remember we have an algebraic way to write on that? Remember how do we write down perpendicular in an algebraic way? Not cross product, a dot product. That is the algebraic way to write down the perpendicular condition we need for the plane. And that is the equation for the plane. Well, although it looks very concise, but what it really means is x minus x naught, y minus y naught, v minus v naught, and the vector is orthogonal to n, which means if you times corresponding components add together, you get 0. Right? So let me write down more clearly. It means n1 x minus x naught plus n2 y minus y naught plus n3 z minus z naught equals 0. So that's the equation for the plane. Right? So let's see our example over there. Suppose you have a plane like this triangle. You have a 1, 1, 1 here. You know, which means the segment, the intercept is 1, 1, 1 on each axis. So you have a triangular corner piece. Right? Let's find out the equation for this plane. So you have to pick a point R0, which is pretty easy, because you have 3 choices. You can pick any one of them. Right? Let's do this one. Let's do this one. Okay. So the harder part is, what is n? Well, n is a vector that is perpendicular to the plane, so there will be something like this, like that. Right? Can you imagine? You have a 3D corner, something pointing outwards from the origin. Right? We can find out in a systematic way, but let's say use symmetry. Can you tell me what is n? n has three components, x, y, z. By symmetry, which component is larger? Suppose you have a corner piece like that. They should be all the same, right? Because x, y, z, they are same intercept. So n should have three components that are the same. Well, if they are same, then it doesn't matter you call it 1, 1, 1 or 2, 2, 2. Because if you change 1, 1, 1 to 2, 2, 2, it means everything is double. And for the equality, it's the same thing. Right? So we can just name it 1, 1, 1. Because you get an equivalent equation if you change to 2, 2, 2. So, by the way, that's also true for a line. If you change the v, the direction of the line, to double, then your equation is just, just as if your ant is moving at a double speed, but you get the same line. Right? And here, if you double your ant, it means this is double, but the plane is still the same. Okay, so the lines, the length, or you can say the magnitude of this end doesn't really matter, so long as it's correct direction. Right? So now let's write down the equation. Since this is a 1, 1, 1, I can omit this n. I just write down x, y, z part. Right? Let's try it. X plugging this into that equation.
Minus 1.
Minus 1. Oh, right. So you can just move them around to get this simple equation. X plus y plus z equals 1. All right? Okay, so let's try something a little bit harder. Suppose you have a 3-point in space. Let's say this is -1, -1, -1. This is 1, 2, 3. And this is 0, 0. Let's put it in origin to make it a number easier. Right, then these 3 points will form a triangle. Well, this is not drawn very well. It should be down there, but anyway. Just have 3 points. Okay? And this triangle is certainly in the plane. Right? Let's find out the equation of this plane. Can you find the equation of this plane? What do you need to determine this plane? R naught and at the end, right? The normal direction. And you have a particularly easy R naught, right? What is R naught?
The origin.
Yes, because we have it all 0. So R naught is anything in the plane. So this is particularly easy. And n is the real challenge. How do we find out n? We don't have the symmetry anymore, right? So n would be some direction perpendicular to this plane. How do you find out n? This time it's cross product. A dot product will give you a number. You need a vector. And if you remember, I said if you do a cross product, you will get a vector that is perpendicular to the original 2 vectors. Right? And that's exactly what we need. You can find out, you have a triangle, right? It has 3 sides. You can pick 2 sides. And their cross product will give you a vector perpendicular to both of them. and there's only one vector perpendicular to both of them, it's a normal direction. Right? So we can use cross product to find out n. Okay? So let's pick two vectors. Let's say this one and that one, because it's easier because it has 0, right? So let me call this one u and this one v. So let's do it. A u cross v. So let's find out u and v. What is u? I start from origin, so it's just the n minus the beginning, right? The beginning is the origin, so it's just that. And what is v? 1, 2, 3. Right? So let's find out the cross product. That's something we just did, but not for this particular vector, right? Right on the second row, which is -1, -1, -1, and this 1, 2, 3. All right, let's find out the three numbers. And before, let me write out minus sign in the middle in case forget. So what's the first number? This cross, right? Be careful, there'll be a lot of negative sign. I have to cancel that. Yeah. What do you get? You get -3 minus -2, which means -3 plus 2. Right? And for the second pair, what do you have? -3 minus -1. So it's -3 plus 1, but be careful, there's another negative sign here. And the last one, you have -2 minus -1. All right, so we have a bunch of negative numbers. -1 is also -1, and it's -2, it becomes 2. Okay. All right, then we are ready. Just plug into that formula, right? So let me. That's really nice because this is all 0, so you don't have this x, y, z naught, right? Just n, y, z. It's just n, y, and 2. So -1 times that, which is x, then plus 2 times y minus z equals 0. That's it. So the plane has this simple equation. Okay? So you can see the equation for the plane is based on the dot product. And to find out the normal direction, we need a cross product. That's why they are both useful when you deal with space, plane, and other objects. Okay? All right, let me see. The last topic we review is about distance. Distance. We know the distance between 2 points, right? Let's say this is a -1, -1, -1. This is 1, 2, 3. You remember how to find out the distance? It's just the norm of that vector, right? The vector is difference, and distance is just that. The distance equals the square root of the difference squared, 2 squared, 3 squared, 4 squared. That's same as the vector's length. But if you want to find out the distance from a point to a plane, it's harder because you need to find out the foot. Well, you don't really need to find out foot, but conceptually you need to know where this point, then find out the distance. Right? But you can get around that. You don't really need to determine this point. Let me tell you how. Suppose you know the plane. Say the plane is r minus r, let's say r naught. Like that. Okay. And if you are so lucky that this r naught happens to be the foot, well, then it's easy just to find the distance. This is the distance, let me call it p. Okay, let me say it's x, p, y, p, z, p. If this r naught happens to be this foot, then it's just distance between 2 points, right? But usually you're not so lucky. R naught is an arbitrary point in the plane. So you know the normal direction, which happens to be this, right? Because this has to be perpendicular to the plane. So this is the normal direction. But r naught is any point in the plane. So how do you find out distance? Well, there is a property. Say if you do the dot product, this, which is this vector here, and you dot it with n, then you will get the length of this, sorry, not the length, the projection of this onto the normal direction. I skipped something, maybe I have to review it now. This means the norm of the length, no, sorry, the norm of the vector. A few minutes ago, I said if the dot product equals 0, then it means they're perpendicular, right? But what if they are not perpendicular? Say this is A and this is B. Suppose the angle is not 90 degrees. Then if you do A dot B, what do you get? Does anyone remember that? It won't be 0, but it will give you something related to this angle. Yeah, it's a number, but that number has something to do with the angle. No. If theta equals 0, sorry, if theta equals 90 degrees, then you'll get 0. Right? Do you remember a function that can change 90 degree angle to 0? A trig function? What trig function will turn 90 degree into 0? What trig function do you know? Right, there are only, say again?
Sine theta?
No, sine 90 degrees is not 0. Cosine, right? Cosine 90 degrees is 0. So this will be proportional to cosine theta. And it's not just cosine theta, because it also has to do with the length and A and B, right? If A is longer, then A dot B would also be bigger. It turned out to be the length of A and B, the length of A times the length of B times cosine theta. So if cosine theta, if theta equals 90 degrees, then you get 0. If theta, let's say the special case, if theta equals 0, then what is cosine theta? No, cosine 0.
1.
Yes, you get 1, right? So suppose A equals B. The same thing. Then what is A dot B? This means A dot A itself, right? Which means A1 squared plus A2 squared plus A3 squared. And what is that? That's exactly A norm squared, right? Because A norm is the square root of that. So if you have A and B are the same, then this is just A norm times B norm times 1, which agree with cosine 0 equals 1. So that I'm explaining why you have this A norm and B norm there, because that's what you need when you say equals 0. Okay, so you have this formula which tells you something about the geometrical meaning of A dot B when they are not perpendicular. Alright? And that's what we can use here. Suppose this angle is theta. Then if you do the dot product of this and that, then you're going to cosine theta, right? And what does cosine mean? It means projection. Right? If you do this right triangle here, you can see the cosine theta of will give you this over that. Right? And that's exactly what we need, because all we know is this vector. Now if we know the cosine theta, then we can get this vector's length. And that is the distance. Okay? So what I mean is this. If you sorry, I cannot write it here. Out of the video. If you do this B minus R dot product, right? Then according to our formula here, it will be the length and the length of n times cosine theta, right? And what is this? This is the length of this vector. If you times cosine theta, what do you get? You get the distance we're looking for. Right? So this part is the distance we're looking for. So if you do the division, the dot product divided by the norm of n, then you get the distance. The formula says the distance from the point to the plane is that. Okay? The denominator is the norm of n. Suppose n equals 1, 1, 1, then it is the square root of 1 plus 1 plus 1. Right? And the numerator is particularly interesting, because if you compare this with that, what do you see? That's the same thing, except you replace r by the point. Right? Which means the numerator is nothing but what you get when you plug in your point into your equation. And that's really interesting, because what if your p happen to be in the plane? Then distance has to be 0, right? And that is true, because you plug in your p into that, you'll get 0. So 0 over something will still be 0, right? And if p is off the plane, then this is not 0 anymore. Yeah, because I mean, if you plug in p into that, that's not 0 anymore, because it's not in the plane. So you get something non-zero. Okay? And by the way, if you want to write a distance, you have to take absolute value, because this number could be negative. Because cosine angle could be negative number, right? Cosine pi is -1, like that. So you have to take. Oh, sorry. When do we end? 20, right?
Yeah.
Okay. So anyway, then that's it. So this is the formula for that. And we can. So see you next Monday.